All right, today we will be talking about the basal ganglia. This circuit always caused problems for me as a med student and know many others, so I'm going to give it a try here, explaining it as simply as I can. As you know, the basal ganglia is responsible for coordinated movement, and the big structure here at play we're going to focus on here is the thalamus. So I like to think of the thalamus as always excited. Have that little lightning bolt here, it's always excited, it always wants to stimulate the cortex. And when it stimulates the cortex here, that will then cause movement, okay? So the thalamus is always excited, it always wants to excite the cortex, and the cortex is always then going to cause movement. And what's interesting here is that, if this was always activated, the thalamus was always activated, we would always be moving, okay? We wouldn't be able to stop. So the thalamus has to be tonically inhibited, okay, to prevent us from constantly moving. And the structure that does that is the globus pallidus internus, okay? And that's going to tonically inhibit the thalamus with the neurotransmitter GABA, okay? So we have that drawn here. You're going to have tonic inhibition of the thalamus, which is going to prevent the cortex and prevent movement, okay? It's not going to excite the cortex, no movement, okay? So, with regard to the basal ganglia, we're going to focus on modulating inputs to this globus pallidus internus, okay? This is our gate, this tonic gate inhibition of the thalamus, okay? Recap, it's going to always inhibit the thalamus and prevent the thalamus from always exciting the cortex and causing movement, okay? Excite this structure here with glutamate, and when you excite this tonic inhibition, okay, you're going to inhibit the thalamus. It's just this pathway right here. If you want movement to occur, you need to inhibit this structure. Okay, you need to release the thalamus from this tonic inhibition. Okay, and we're going to do that with GABA. So if you have GABA here, you're going to inhibit the globus pallidus internus, and that's going to release the thalamus. Thalamus is free now to excite the cortex and cause movement. So we're going to focus on these inputs here. How exactly do we get this inhibition of this gate? So here's a structure we're going to look at, the striatum, also called the caudate. And the striatum is going to directly cause this GABA release, inhibit the globus pallidus, and release the thalamus, okay? It's going to do that with some acetylcholine. Acetylcholine is going to cause the release of GABA. GABA is going to inhibit this globus pallidus internus, and when this is inhibited, the thalamus is free to cause movement. It's simple enough. Now, this pathway down here, how do we excite this gate, okay? If we want to prevent movement from happening, we need to stimulate this structure to inhibit the thalamus. This one's a little bit trickier, okay? So we're going to, in order to, look at this and see how we get this excitatory glutamatory input, we're going to need a structure called the subthalamic nucleus, okay? It's going to be down here. It's going to be causing this structure to inhibit the thalamus, okay? And the subthalamic nucleus is stimulated also by the striatum, except the pathway is a little bit more indirect, okay? Striatum is going to release acetylcholine, cause the release of GABA, okay, same as up here. But we don't want to inhibit this subthalamic nucleus. If we inhibited this, then we would have nothing to stimulate this globus pallidus internus. And if you don't stimulate the globus pallidus internus, you can't block the thalamus, okay? So this subthalamic nucleus needs to be stimulated in order to block movement. So when the striatum releases acetylcholine, stimulates GABA, it is going to inhibit a structure called the globus pallidus externus. And this structure's job, this is a little bit confusing, but this structure's job is to inhibit the subthalamic nucleus. Okay, so if we don't have this to inhibit this structure, this subthalamic nucleus is free to stimulate the globus pallidus internus. That, in turn, will block the thalamus and block movement. Okay, so this double negative here, two negatives make a positive. We're going to stimulate the globus pallidus internus, which will block the thalamus. So, a little bit confusing, but let's look at how dopamine fits into this entire pathway here, and this is the basal ganglia. So dopamine, we know, released from the substantia nigra pars compacta, and it is pro-movement, okay? So dopamine is pro-movement. So what does that mean? That means somehow we're going to stimulate the thalamus, and we're going to get movement, okay? That means we have to block the globus pallidus internus. Now, here we have a structure, a D1 receptor for dopamine in the striatum. So dopamine will be released from the substantia nigra pars compacta, bind to the D1 receptor, and that's going to stimulate this pathway. Okay, so you're going to get that release of acetylcholine, you're going to get the release of GABA, you're going to inhibit the globus pallidus internus, thereby disinhibiting the thalamus. Okay, this is inhibited, thalamus is free to move. Direct pathway, because it's pretty simple, right? This dopamine binding is going to stimulate this direct pathway here. Boom, GABA inhibits the globus pallidus. Now there's also an indirect pathway, this one down here, where dopamine works. So you have a D2 receptor. Dopamine again released by the substantia nigra pars compacta. Okay, it's going to bind here. But instead of stimulating, as it did up here, this D2 receptor is going to inhibit the acetylcholine release. So if you're blocking this activity over here, okay, you're not going to get this GABA release. You're not going to inhibit the globus pallidus externus, okay? This is blocked. So this globus pallidus externus is free to inhibit the subthalamic nucleus, okay? Free to inhibit the subthalamic nucleus. This is blocked. Subthalamic nucleus cannot stimulate the globus pallidus internus, and therefore there's no inhibition of the thalamus, and you get movement, okay? So what do these two pathways look like together, direct and indirect? Let's see. You're going to have dopamine binding in both places. You're going to have stimulation here, inhibition here, okay? Going to have inhibition of the subthalamic nucleus. You're going to have inhibition of the globus pallidus internus, and the thalamus is then free. Okay, remember, this is inhibited, thalamus is activated, you get movement. So that's it really in a nutshell, a little bit confusing, but just one last important thing to point out, a clinical correlate about Parkinson's disease. So Parkinson's is degeneration of dopaminergic neurons in the substantia nigra, okay? So if you don't have these inputs here, D1 and D2, you're not going to have this pro-movement, okay? You're going to lose this entire pathway here, okay? And Parkinson's occurs when you lose about 75% of these neurons, okay? That's when symptoms start happening. So if you don't have these inputs up here, okay, you're going to lose this inhibition you have over the globus pallidus internus, okay? You're going to lose this inhibition of acetylcholine. You're going to thereby have this inhibition of the globus pallidus externus, okay, indirect pathway. And you're going to have this activation of the globus pallidus internus, and that is going to inhibit the thalamus, okay? And by inhibiting the thalamus, you lose movement. You do not have movement. All right, so that is it. I hope this was helpful, and thanks for watching.